Right, that squared. So it's 12x squared times 12y squared minus negative 4 squared. That's what we have, yes? So you can see that d actually depends on x and y, right? It has x's and y's in here now. So what I'm going to do is first look at my first critical number, which is 0, 0. So is it all right if I write this d of 0, 0? Does that make sense to you that what I'm doing is calculating d at this point? D of 0, 0 would be what? Negative 16? Negative 16. What does that tell me? I have a saddle point. I have a saddle at, what's the point? 0, 0, and I want the triple, so plug 0, 0 into this. 1? That was easy, right? 0, 0, 1? Guaranteed, that's a saddle point. It's neither a maximum nor a minimum. Now we're going to do d of, let's say, 1, 1. This would be, what, 12, 12, so 144 minus 16 again. This is bigger than 0. Do you agree? Okay, when it's bigger than 0, right, you then have to go and check something secondary. You have to check that fxx and see if it's positive or negative. Okay, when it's negative, it's saddle point, you're done. But if d is positive, there's two possibilities now. So all you have to do is come back to this piece right here and just do a visual real quick. Right, that's fxx. That fxx is equal to 12 is also positive. So we should have what here? Local min? Just going to check something real quick. Yeah, that's good. So we have local min at the point 1, 1. You already did it? Is negative 1? And then you go through. Understand where you got this from? Just plug 1 for x, 1 for y in there. You should get negative 1. Now the last computation, d of negative 1, negative 1. Isn't it going to be exactly the same? It's exactly the same as this. We're going to get a 12 because you're squaring x. It was 12x squared, 12y squared. So you should still get 12 times 12 minus 16. It's still positive. And then that piece that we're supposed to inspect now, this piece, is still positive, right? So another local minimum. So local min. Local min at the point negative 1, negative 1. Is it still 1? Yeah, turns out negative 1 still turns out to be the same, I believe. Any questions? Sure? So if I graph this function, right, this surface, what I'm telling you is that I may not be able to find the highest and lowest points on the graph. Okay? But what I can tell you is locally where you have some important things happening. I know you have a saddle point at 0, 0, 1. I know that you've got local minimum at 1, 1, negative 1. Another one at negative 1, 1, 1. So here it is. I'll erase this stuff here. There's the graph right there. Now, it does not stop right here, okay, along that. It just keeps going up, but I mean, the graph had to cut it off somewhere, right? So there it is. And we have our saddle point, which you can't see right here. So what I'm going to do is I'm going to pull the surface out a little bit. Maybe I shouldn't have. That didn't help. There's that saddle point. See the saddle point in there? Do you see it? And then we have our local minimums. So what are the things that are going to be the most complicated parts of these problems? Taking the partials, and especially the part where you set the partials equal to 0. That might be the part that comes back to haunt you. Solving equations. Because pretty much anything's on the table right here as far as solving equations. They could be polynomial equations, they could be trig equations, they could be exponential, logarithmic equations. Anything can pop up here. And the derivatives could get ugly. Why don't I give you about 5-10 minutes to see how much of this you can get through in 5 or 10 minutes. At least try and knock the partials out. Get all your partials listed out. Then go try to set those partials equal to 0. See if you have any luck. That sound good? Can everyone see it? Is it working pretty straightforward, or are you running into some issues?
Are we supposed to run into issues?
I don't know. I haven't worked it, so I'll work it over here while you're doing that. I believe those are your groups of partials. How many of you got those partials? Yep, so we're at least that good with it? Yes? How many of you have started trying to set the partials equal to 0? Having any trouble? No? For someone who started working these set equal to 0, want to tell me how they went about it? Yes? Where?
F of y.
Oh, sorry. I wrote the wrong thing. Thank you. X, thank you. X cubed minus a. So don't mix these up or you'll be in trouble. So look, this one and this one, those are the two. Okay, so yeah, this is going to be real straightforward now, right? Because you can just solve this one, right? This is x cubed is 8, which means x must be what? 2 and only 2, right? Not plus or minus? Because you're taking a cube root on both sides. Cube roots, you don't have to do plus or minus. So this tells you, look, for this one to be true, x has to be 2. Has to. No options. Once x is 2 here, you go over here and get y. So what do you get here? 3, 2 squared y plus 24 times 2 equals 0. 12y plus 48 equals 0. So y is -4. Y is -4. So there's only one critical number, right? This is it. This is the only critical point we have to worry about. But we have to compute d at that critical point to figure out if it's saddle, max, min, whatever. You ready to compute d? All right, so let's look at d. D will be the second partial, this one right here. So 6xy plus 24 times, fyy? 0 minus 3x, that quantity squared. And what I'm going to do is this won't matter because this is all going to be 0, right? And this, when I plug in x is 2, right? That's going to give me a number squared. It's going to be minus a positive number. It's going to be a negative number, isn't it? So that's less than 0. So what do we have? Saddle point. We have a saddle point. It is the point 2, -4, and then whatever you get when you plug 2 and -4 into this, right? Anybody do that yet or no? It's all right if you haven't. I have it down here. 48. Should be 48. And that's it. You do not have any local maximums or minimums. Good or no? Here's the graph. Weird looking graph, huh? It's kind of cool looking. If you looked at this graph, you might think that maybe you don't have a saddle point, or maybe you have more than one, or I don't know what you would think, but you can't argue with the mathematics. There's a saddle point right there. We're not going to, it's not open for debate. Okay? There it is.
Can there be 2 saddle points?
Of course, yes. You can have more than one. You can have more than one local max, more than one local min. Here's a pimple function, right? There you go. So let's see if we can do this one. I'm waiting for an interesting problem to come up here. Surely it has to be more complicated at some point. No? These derivatives might be a little more complicated. Because of time and because you have homework that you can do to practice, I'm going to go through these. What's the partial of f with respect to x? It's the whole thing times negative 2x. So derivative of e to anything is itself, but then derivative of what's up here with respect to x is negative 2x. So I'm going to write negative 2x e to the 4y minus x squared minus y squared. Questions on the partial with respect to x? Now, again. Uh-oh. Now things can get more complicated, right? Now you have to do the product rule because you actually do have a product, right? Right here, you have a function of x and another function of x, and you're multiplying them, so you have to do a product rule. What is the derivative of this with respect to x? Negative 2, right? Negative 2 times e to the 4y minus x squared minus y squared plus, continuing with the product rule, the derivative of this, which is, we just did that, right? Negative 2x. So it's going to be negative 2x times e to the 4 minus x squared minus y squared. Am I done? A little bit more. What? I missed what? 4y. Yes, I missed my y, didn't I? Times negative 2x. So you have to finish the product rule off, right? You got to remember where we were there. That's a mess, right? See if we can clean that up at all. See anything that those both have in common? Because there's like two terms, right? Here, here. Anything they both have in common? How about negative 2? They both have a negative 2? They both have an e to all that junk? So why don't I pull a negative 2, e to all that junk out? When I pull that out, what am I left with? So what would be left here if I pull that out? A 1. Okay. And what would be left here if I pull all that junk out? So I pulled one of the negative 2's out, so I'm left with x, negative 2, so negative 2x squared, and that's it. There you go. It's a little cleaner. All right. Moving along, partial with respect to y is it's itself, right, times the derivative of what's up here with respect to y, which is 4 minus 2y. So I'm put that out front, 4 minus 2y, then all that stuff. That's your first partial with respect to y. And then again, take the derivative. Am I going to have to worry about product rule? Yep. I'm going to have to do product rule again. So the partial with respect to y again is derivative of this with respect to y, which is negative 2. And then all that junk, right? E to that junk. Plus, now the derivative of this, which is, we did that a second ago. It was 4 minus 2y, e to all that junk again. See how this is getting a little more complicated? Am I done? Times 4 minus 2y again, which was the stuff out front. Can you clean that up? Yeah? What would you like to pull out of that one?
Just the
Just for now, do you want to pull the e? Just the e? Just for now? Okay, let's just pull the e junk out. E to the 4y minus x squared minus y squared. I'd be left with, let's see, over here, negative 2. And over here, 4 minus 2y, twice. So plus or minus? Plus. 4 minus 2y squared. That's what it would look like. All right, one more derivative for me to try and get. Partial of f with respect to x followed by with respect to y. Partial f with respect to x followed by y. So that's this one up here with respect to y. What's good about that? If I do that, what? Do I need product rule? I don't, because this is not a function of y. So I can ignore that as a constant and just take derivative of that with respect to y, which is itself times negative 2y. No, 4 minus 2y, right? So it'll be this times 4 minus 2y times that. So negative 2x times 4 minus 2y times e to the 4y minus x squared minus y squared. Woo! All right. So if you can't do partial derivatives, it's going to cause some trouble, right? This is why on the next test, I probably won't give you a problem where I say, hey, what's the partial derivative of this? I'll just ask you to find local max and min. You'll have to do it, right? You'll have to do multiple partial derivatives. So you'll have to show you know how to hold something constant and how to apply a chain rule and a product rule at the same time. And it's all kind of tested within this one problem. All right, all that was fun, but why did we do all that? We need to find these critical points, right? So we need to set our partials equal to 0. Partials equal to 0. I'm going to keep this up here. I don't want to erase this. This is my fxx, right? This one was my fyy. And this one down here, I'll just leave. So I'm just leaving these on the board so I can refer back to them. I just erased. Damn it. I didn't want to erase that one. OK, let's do this one. So I'm setting partial of f with respect to x equal to 0. That means I'm setting negative 2x e to the 4y minus x squared minus y squared equal to 0. Now that looks like a complicated equation, right? Looks rather complicated. But what can you tell me about this factor, this part of it? Can e to anything ever be 0? You can never make e to any number 0, can you? So if that's never 0, then you can ignore it completely. So this doesn't matter. So all you're really looking at is negative 2x equals 0, which means x is 0. That's nice. That's good to know, right? And then the other partial with respect to y, I didn't write it, or I erased it, because I was thinking ahead, planning ahead as usual. Let me see. It was negative 2y e to the 4y minus x squared minus y squared. That was it, right? No, 4 minus 2y. That's what I meant to say. See, you didn't see the parentheses there. It's right there. That was our first partial, right? We set this one equal to 0. Again, same thing. That e part, this whole factor, can never be 0. So ignore it. 4 minus 2y equals 0 means y is 2. So I only have one critical number. It's 0, 2. You all with me? 0, 2. I'm going to erase everything I just had there because I'm going to keep all this stuff up here because I'm about to compute d at that point 0, 0, 2. So my critical point is the point 0, 2. And now I'm going to get D. Now, let's do D at 0, 2 right now. Let's see if y'all can keep up with this. D at 0, 2, because I don't want to write out D. Because if I write out D, aren't I going to have to write, I'm going to have to write this times this minus this squared, right? I don't feel like doing that. Instead, what I'm going to do is I'm going to plug in 0 and 2 into each of these. So first I plug 0 and 2 into this, right? 0 for x, 2 for y. Let's see what happens. 0 for x, this is just going to be what? A 1. Okay, that's a 1. Y is what, 2? So that's 8 minus 0 minus 4. So e to the 4. Negative 2 times e to the 4 times 1. So negative 2 e to the 4th. Anybody have a question on how I got that? Now I need to plug 0, 2 into this. E to, we already did that. Didn't that come out to be e to the 4? E to the 4th. Let's see. Y is 2. Hey, check it out. 2 times 2 is 4. 4 minus 4 is 0. 0 squared, 0. And voila, I've got another negative 2. Negative 2 times e to the 4th again. Yeah? They won't always be the same. Minus, now I plug in 0, 2 into this. And what happens? It zeroes out. Because of this negative 2x, that x is 0. Everything else doesn't matter. You just get 0. And what is this telling you? E to the 4th is positive times negative 2. So this is a negative number. This is a negative number. 2 negatives multiplied to be positive. This is greater than 0. Since it's greater than 0, what do you now need to check? This one. And it was negative, right? So we have a D greater than 0 and a negative. So we have a local max. We have a local max. Understand? Local max. It happens at 0, 2, and then you have to plug 0, 2 into the original function, e to the 4th. That's it. King of the mountain. What do y'all think? I mean, yeah. That derivative was a little bit uglier, right? That required a little bit more attention to detail. I did your homework. I didn't do all the problems, but I did number 11. I shot that video for number 11 3 times. Because the derivative, I just kept on butchering the derivative and plugging things in. I was trying to fit everything on one board, and it was driving me crazy. So I was losing track of things, and it was a mess. So I think I finally got a decent version of it. So just be careful. All right, let's see if we have any more. Ooh, that one looks interesting. You want to mess with that one? All right. I'll give you another 10 minutes. This section, before you dive too hard into that, this section, we're finding right now we're finding local maximums and minimums, right? I have not restricted the domain. And I was telling you in the very beginning of class, when we look in Cal 1, we have a cubic function. We could not restrict the domain and look at local max and min, or we could cut it off and then look at max and min, right? The second part of this section is us restricting the domain, cutting it off. We haven't started that yet. We got to make sure we can do this part first. All right? This is I think this is going to be a good exercise for you. Just a little hint there. I rewrote the function in a way that might make it easier to take derivatives.